My name is Steve Marr with Risk Management Professionals, and we're going to get started with our webinar. Basically, this is a continuation of our HAZOP facilitation seminar series, and this is something we're doing in modules. This is module number 4. As you know, Risk Management Professionals is an engineering consulting firm with a background having been involved with PSM and RMP issues even before they were promulgated we've been doing it since the mid-'80s. We do a lot of work for a variety of facilities, offshore facilities, platforms, processing facilities, onshore exploration production facilities, refrigeration facilities, very wide range of facilities that have to meet these requirements. One of the cornerstones of meeting these requirements is understanding the hazards that exist at a plant site. For that, there's a variety of tools that we've been examining in previous modules, things like what-if, checklist studies. At the very high end of the spectrum, there are things like fault tree analysis and event tree analysis. Well, the workhorse of the business for dealing with PSM, RMP, SEMS, and SEMP issues is hazard and operability studies. So that's been the main focus of our seminar, this seminar series, and our main objective is to help you get enough background so that you can facilitate and do good quality HAZOP studies, which again are the cornerstone of meeting these regulatory requirements, understanding the hazards at your plant site, and of course the ultimate objective, which is protecting the health and safety of the individuals at your plant, protecting the environment, and also the community around you. So that's what we're doing here. Before we go any further, I'd like to talk to you a little bit about logistics. As for our previous modules, this is we're using WebEx as our webinar broadcasting mechanism. It provides two-way communications, which during the course of the presentation, you will be muted so that any activities that you have going on your end are not broadcast to the rest of everybody tuning in. Oh, by the way, you're recording this, right? Excellent, excellent. We're recording it too so people can come back to later and catch up if they miss various modules. So this is something that as we progress, we're going to be doing a presentation that focuses this morning on a variety of issues associated with defining good causes and also safeguards associated. Good morning, and also safeguards associated with the HAZOP study. That's going to be our main focus today. We're going to follow that with a little workshop to kind of reinforce those types of activities. And then we're going to go ahead and close with the opportunity for questions and answers. The questions can be posed to our producer, Nicolo Tromba, either during the course of the presentation if you feel there's an important topic that needs to be brought up, or after the presentation and workshop are done, it'll be an opportunity for you to ask questions and bring up additional points. At the conclusion, if there are no further questions, we'll be providing you with the answers to the workshop. So again, we'll progress starting with the presentation. At any time, if you need technical assistance, either let our producer, Nicolo Tromba, know that, or go ahead and call our main office, 877-532-0806, or our local number, 949-282-0123. All right, so where are we? Basically, the key topics that we've already covered in Module 1 was the regulatory requirements, overviewing it, and doing a little case study. Module 2 was the HAZOP study mechanics, quality tips, consequence analyses. Our last module that we shared with Judith Sakairos was PHA preparation and also what to do with good quality P&IDs. Key topics for this item, or for this module, are going to be the details of how to construct a good quality HAZOP study scenario, and also some workshop to reinforce key points on defining causes and safeguards. And so this is part of the package that was sent to you last night, by the way, and this tells you what modules are coming up so that you can schedule accordingly. Okay, so without further ado, I'd like to switch over to our presentation this morning. Okay, we're on Module 4A. There. In fact, I'm going to ask you, if you don't mind, just reach over. When I flick that, if you reach over and just hit the space bar or the page down key, that'll be good. Okay, so what I'd like to do is talk about scenario details. Real good. Are you having trouble? Okay, it's a custom show. Okay, so you do slideshow, custom shows, and 4A show. Okay. All right. Okay, that's good. Okay, so, all right, is it showing right now? All right, that's as good as it gets. That's fine. All right, so I'd like to talk about the HAZOP study scenario details. And just to let you know where we're at, the topics in previous modules that we covered were a history and background and regulatory basis, and how HAZOP studies came about, what their requirements were, required PHA characteristics and available tools, choosing the optimal PHA approach for the project, details in the HAZOP study, maximizing the usefulness in the HAZOP study, quality tips, consequence analysis basics, preparing for PHA, and also quality P&IDs. For this current module, key topics, okay, good. Key topics, good. Okay, key topics for today are going to be correlating the HAZOP study scenario contents with PHA objectives, key implementation steps, defining causes. I'll tell you what, this is going to be, I'm going to have to take 30 seconds to retool here, guys. Excuse me. All right, what we're going to do is I'm going to pull this. And thank you for your patience. Okay, key implementation steps is what we're going to talk about today. How to define key causes with respect to human error, control system malfunctions, mechanical failures, common mode failures we're going to talk about, special topics and tips, unusual operating modes. Do me a favor. We're going to take another 30 seconds here, guys. Sorry. long has the microphone been off?
I guess about 20 seconds.
Oh, okay, that's not too bad.
This one was acting up and I was getting out all the time, but
All right, we've had a variety of technical malfunctions today. We're fully good? Okay. All right, so for those of you who could read lips, you were really tuned into what we're talking about. The key thing is defining causes that really help the team out and really uncover potential hazard and operability studies. Common mode failures, things that can be a single mode failure that can have multiple impacts. Unusual operating modes. These are things, if you have abnormal operations or different modes of operation, if you don't handle them right, it can really eat up a lot of the team's time. So being able to focus the team, handle the different operating modes properly, that's really key to the success. And not only can you save a lot of time, but you can really improve quality. Defining safeguards, also quality control. Again, the most important thing is to get a good quality HAZOP and keep the team focused. As a facilitator, you want the team focused, you want to keep the team moving to make sure that you can uncover what you have to uncover, and then but not let them drift off, get distracted, or basically lose their attention, or even if they leave the meeting. These are really bad if it drags on too much. So you've really got to keep things focused. Then, of course, we're going to do a little workshop. Okay, first of all, I'd like to put things in perspective in terms of overviewing the HAZOP study and what the key objectives are. Again, let's look at the big picture. There's a variety of things that can go wrong at your plant site. Some are going to be high consequence, low probability, and of course not very important because even if it's catastrophic, it may be nearly incredible. Other things can be high probability or very frequently occurring, but very low consequence. Things like operational upsets may also not be all that important to look at. So what you're using the HAZOP study for is to look at the likelihood of the event, the consequences of the event, as a measure of importance. Things that are higher on the risk curve, as you look at the line that's going through the center of your screen on the graph, risk is increasing. So you're really looking for those things that have enough consequences and enough likelihood to make them important. Once you focus on the important issues that you can then identify, are there design fixes, are there things that need to be done to make improvements? So it's all about understanding the probability, understanding the level of consequences. That's what risk is, focusing on the high risk events, and then focusing on your design efforts, your operations attention to making those risks as low as reasonably acceptable. A quick example, here's a high pressure vessel on level control, a pretty typical setup for a facility. This is a representation of how it functions. This is basically a snapshot of a PNID. The whole idea of a HAZOP study is to translate that design representation into what can go wrong with the system so that you can uncover weaknesses and address those high-risk scenarios. The main approach uses a deviation matrix. The idea is to combine guide words and process parameters and look at deviations from normal operation, things like decreases in flow, increases in temperature, decreases in temperature, things that may lead you down to a path of having a hazard at the plant site. This is a very cyclical approach. You've got a very regimented definition of nodes, application of process deviations, causes that are credible that you want the team to look at, consequences associated with those causes, again, ultimate consequences that take you down a path of how bad can it get. Then with that scenario, understanding of the scenario, identifying the safeguards that function as a buffer between those causal events and the ultimate consequences associated with that scenario. You use the same approach, cycle through it very methodically, and then what you do is use that to identify potential system weaknesses. It's represented typically in a tabular form where the records are kept with causes, consequences, and safeguards documented. A risk ranking approach is used. We've talked about that before to help you understand which of the scenarios that are higher risk, and if there are weaknesses, what recommendations might be applied to it to remove those weaknesses. So that's our key objective, is to go from that design representation to understanding it from a failure representation to documenting it, uncovering weaknesses, and then having improvements. That's where the rubber meets the road in terms of improvements that may be needed to remove weaknesses and make sure that it's safe enough for employees, the environment, and also the community. So key implementation steps. That's the real magic, and that's what I want to focus on today. 50% of the success of a HAZOP study is really preparation. The facilitator understanding the technology, reviewing the drawings, getting key templates in place to help guide the team. It really helps quality. It helps make sure the team's time is properly utilized and effective, and it also keeps the session time minimized. Now, depending on what your objectives are, preparation can save a lot of time, but obviously if you're using a contractor that's out there and you're basically a hired gun as a facilitator, they're going to need a little bit more time to prepare, but you're going to more than make up that extra cost or associated with that additional resource utilization by saving a lot of time from the team where you've got maybe 6 to 8 people sitting around. Any hour that you save of that team's time translates into a big savings in terms of the overall cost of the HAZOP study. We talked last time about the timeline for preparing for a PHA. You've got to start well in advance to define objectives and scope, make sure you got the right people invited, the tools arranged, the proper venue, getting the key information. Well, a lot of the key information comes about because a HAZOP study is usually used to trigger progress for a capital project. It usually tends to come about during the last weeks right before the HAZOP study is scheduled. At the bottom part of your screen, one of the final things that happen is you finally get, as a facilitator to prepare for the HAZOP study, the final P&IDs, or the P&IDs that are going to be used for the HAZOP study. Once you get those, you can actually do the serious preparation in the last stage right before the HAZOP study, defining the nodes right beforehand, preloading the risk ranking matrix, making sure your design intentions and consequence categories are well defined, and binning various types of events as appropriate. Making sure your deviation matrix and template are defined and also preloaded into whatever software package you're using. Making sure causes are populated. We'll be focusing on that a lot this morning. Making sure you prepare training materials, reference materials, getting final copies of the P&IDs and process flow diagrams ready so that the team can be ready to go when you're starting your HAZOP study. So let's talk about defining the causes. This is an art, basically, and it is so important, and it makes such a difference in the quality and the amount of time that you use for the team. It's really important, and that's what I want to focus on for this module. Key types of causes. What can go wrong in a plant site? Usually they're categorized in 3 areas: human error, control system malfunctions, or mechanical failures. The reason why they're ordered like this is human error, people making mistakes, whether it be directly pressing the wrong button or not maintaining equipment or something else that they missed in terms of the plant operations. These are things that are whether they're subtle and they precipitate into something bigger or a direct causal event to the accident that occurs. All those are very likely. So you've really got to focus on human error and also human factors issues. And we'll be talking a little bit more about human factors issues this morning. I've put some probabilities on this slide also to illustrate how likely some of these things are based on reference values that are in literature and also reference values that are used, taken from the CCPS layer protection analysis. That's what CCPS and Center for Chemical Process Safety layer protection analysis guidebooks is our key reference point for this. So failure to execute a routine procedure in an unstressed and unfatigued fashion, basically 1 in 100 per opportunity of not doing it correctly. The second bullet, failure to execute non-routine procedures or a routine procedure if stressed or fatigued. Basically, you can get a factor of 10 more likelihood of failure because of the stress factors, the fatigue factors, or basically if they're not executing the procedure on a routine basis. Especially if it's especially critical for batch processes or unusual operating modes, human errors are especially critical, and you've got to pay very critical attention to those. For control system malfunctions, basic process control systems, instrument loop failures are quoted as 0.1 per year, also out of the LOPA guidebook. These are things that can occur, that do occur. A lot of people take care of that with smart sensors. They take care of it with voting logic and using multiple detectors. A lot of things can be pulled into play, but basic instrument loop failure people usually look at as 1 in 10 years causing a failure. Mechanical failure examples, things like a safety valve opening spuriously, they usually tag that with a 0.01 or 1 in 100 chance per year. Pump seal failures, 0.1 per year. These are the kind of things that can occur and various likelihoods associated with them. These numbers that are put there, again, most of them are out of the Center for Chemical Process Safety Layer of Protection Analysis Guidebook. These are things that are typical screening values, typically conservatively high, just to make sure that you're not missing critical scenarios. How do you deal with that? Again, you're translating on the left-hand side, you see a schematic representation or a P&ID snapshot of a vessel, pump, and level control feature. You're translating that into what can go wrong. The possible scenarios that can come out of that are on the upper right-hand side. Level control valve 1 failing closed. It's a fail closed valve, possibly due to malfunction of the transmitter controller or block valve inadvertently closed. The level control valve can malfunction open. You'd want to look at that during a HAZOP study too. And also, you want to pull out various safeguards. There may be alarms or other features, and those come into play. So again, we're going to translate, the whole HAZOP study translates the functional depiction into a tabular depiction of what possible weaknesses there are. So let's talk about human error a little bit more. Human error, there's various categories of that. Errors of commission, where somebody overtly does something that's incorrect. Errors of omission, where somebody misses a step or doesn't do something. Or errors of intent, where somebody decided to maybe take a shortcut. These are core problems that tend to precipitate other types of specific failures, and these are the kind of things that you can quantify and certainly should be considered for the HAZOP study. The kind of impacts these have, the human error might initiate an event. It might compromise a key safeguard. If there's an important alarm and the operator has to take action, well, that operator action can have some error potential in there. Also compromised emergency response. If something is confusing, if the equipment doesn't work, and the operator has to take some alternative measures, these are all things that can have operator errors come into play. Typical causes, and I'll just throw out some general causes. A diesel air cooler. Okay, what we often do is couple, if an operator error or mechanical malfunction can cause the same type of event, we'll couple that and we'll look at the same event caused by multiple different things. The first bullet is a louver malfunction in air cooler, maybe caused by instrumentation failure or inadvertently closed by the operator. So the operator doing something, if that something can also occur when you do a mechanical malfunction or a control system malfunction, this is a good way to link them together. The second bullet, spare diesel product pump inadvertently activated. Operator doing something, an error of commission in terms of activating a spare pump can cause potential problems. Other things that can go wrong, a bypass valve being inadvertently open, manual valve being inadvertently closed, or potential hazards associated with sampling. All these are types of human errors that you may want to look at during the course of the HAZOP study. What I also want to do is to convey to you the types of human errors that can occur. There's a very nice human factors training course that was recently put on by Cal OSHA, and what I did is I took some excerpts from that. So as the HAZOP facilitator, I mentioned some fundamental human errors and things that you may want to consider. There's a wide range of human factors that can lead to those errors that I wanted to share with you. Direct causes can be opening a wrong valve, pushing a wrong button, failing to follow a procedure. These are errors of commission or omission that can result in a potential hazard. These are things that you want to think about, and as appropriate, either couple them with technical failures or in tandem with the technical failure. When you're looking at human factors or human errors, you want to keep in mind that there may be underlying causes for direct causal events. Poor design, unclear labeling, the layout of the controls, equipment access, improper placement of equipment, lack of maintenance, inadequate training, fatigue, or inadequate staffing. Maybe those are kind of associated with each other too, but all those can be underlying causes that can lead to specific human errors. So during a HAZOP study, you're going to be identifying and looking at specific human errors, but as a facilitator, you'll want to challenge the team to look at potential underlying causes and if there are weaknesses in there that need to be addressed and that you want to flush out as part of the HAZOP study. Some examples of things that aren't too good. I was told this is a photograph from an actual facility. Labeling is poor, trying to find a valve is poor. This is a situation that is very prone to error. I've never seen anything this bad myself, but I have seen situations, especially when you're looking at crude units and you're looking at rundown lines where you can get a lot of crossover connections, where a lot of the configurations can be very confusing, and you've got to be very careful during the HAZOP study to consider those types of events, and during the HAZOP study, or at least as part of the HAZOP study, you'll want to go out and do field walkdowns to kind of take a look at the configuration with the team. Labeling is very important. This is an example of good labeling of piping and a key piece of equipment. Poor labeling. This is something that can lead to human error, contribute to the kind of accidents that are looked at as part of the HAZOP study. How controls are set up. On the left, on the photograph on the left, you've got a system that it's not readily obvious if things are running smoothly or not. On the right-hand side, if gauges, whether they be software controlled or old-fashioned mechanical gauges, if you've got something that gives you a measure of if you're within safe bounds or not easily, they can be much easier to read and decrease the potential for human error. Looking for causal events, again, some of these diagrams, you've got confusion with respect to valves, confusion with respect to buttons. Maybe the buttons aren't labeled, maybe they've been worn off. And also, you'll want to be looking at incident reports. What kind of things have happened, especially if near misses have occurred that have led towards an accident but never quite got there because somebody caught it in time. In the lower right-hand side, somebody not responding properly to an alarm. How many facilities have you been to where you've got multiple alarms going off at once, maybe some that have been ringing continuously because something's out of service or somebody hadn't been doing proper maintenance? An operator's got to keep on top of that, and if all the alarms come in at once and they're not prioritized, it can be awful confusing and decrease the reliability of that safeguard. And while we're talking about safeguards, if you've got multiple alarms, you've got to be careful not to give multiple credit for multiple alarms that just tell the operator to do the same thing. Even if one alarm goes off, it's clear cause, and it leads to the operator taking the correct corrective action, that's fine. There's a certain human error probability associated with that. 2 alarms, if it's clear and it's directly associated with the causal event, can also help the operator rapidly diagnose the problem and take corrective action. But how much extra does 3 alarms, does 4 alarms, 5 alarms, how much more do they help? One of the key things during a HAZOP study is you want to be careful when you're listing safeguards to only list those safeguards that are directly associated with the cause and are contributory towards improving that ability for the operator to respond. So also in terms of physical layout on the screen, take a look at which stove has controls that are clearer. The one in the upper left-hand corner, it's decipherable as long as the labeling is correct and it hasn't worn off. The one in the lower right-hand side hardly needs labeling. There's a direct correlation between the control mechanisms and what you're doing with it. Other problems, matching the job to the worker. If you've got valves that are up in a pipe rack, difficult for people to get to, during an emergency, that's going to decrease the potential for somebody actually taking corrective actions. These are things that need to be considered during the HAZOP study. A typical thing during a HAZOP study, if you're responding to alarms or out in the field, is how much time does the operator have to take the corrective action, and can they effectively do it? Stress and fatigue. You know, most process facilities are run on a 24/7 basis. Have you made arrangements to make sure that operators have enough stuff to do to keep them alert, but not too much to do so they can't keep up with it? Trying to find that balance between stress, fatigue, getting the job done, and also running your plant safely. Some of the things that have come up during when you're implementing process safety management systems is when you're looking at incidents, unclear procedures, not having procedures, communication barriers, lack of labeling. These are key things that do lead to accidents. So these are the things that obviously you want to make sure that you cover properly during your HAZOP study. Other issues associated with operating procedures, again, not having a procedure, not having caution warning statements properly in the procedures, step set of sequence, having procedure titles that don't really match what's doing. And also, we find this a lot, procedures that don't really match with what the operator is doing in the field. The procedures are something that should capture operational best practices and be used as a basis for amplifying those best practices and carrying them through for all personnel. And these are things that you need to be looking for during the course of the HAZOP study. Other engineering standards that you need to be thinking about with respect to human factors: color blindness, visual resolution, stress workload, we talked about that already, alarm prioritization we talked about, automation, and also control layouts. All these things are important when you're trying to either take credit for operator action to mitigate an event, or you're trying to take credit for the operator doing their job to prevent the event from occurring in the first place. So that pretty much covers the kind of things you want to look at for human error and human factors. What sort of things do you need to look at for control systems? The first bullet is a temperature transmitter failing low. A lot of times multiple control actions are coming off the same temperature transmitter, so you don't want to necessarily just list the valves that fail. You want to dig down and make sure that you come to the root control item, transmitter, or other processor that's feeding all this equipment that could fail and cause problems. The second bullet, heat tracing failures. Heat tracing failures that can result in lower temperatures can often compromise equipment, cause freezing, obviously, and also compromise instrumentation. These things need to be considered during the course of the HAZOP study. Third bullet, the pressure transmitter failing high. Again, if you've got a common mode failure of transmitters, these may be very important to look into. And also utility failures, loss of instrument air, loss of power and other control mechanisms. These are also very important to be looking at. Mechanical failures to consider during the course of the HAZOP study. Tube ruptures on heat exchangers. If you've got a heat exchanger, high pressure on one side, low pressure on the other side, you need to be really careful about what the impact is of a tube rupture. A PSV failing open. I don't know how many times the team says, our PSVs don't fail open, we maintain them. Well, if you look at the statistical data of plant sites, their mechanical failures do happen. If a PSV fails open, you want to make sure the system's designed for that. So you want to at least look at it as a credible scenario for your HAZOP study. Check valves failing to reseat. Most people don't want to even credit check valves during the course of the HAZOP study, but if you are, and it's fair that you do, make sure that you look at them as something that is inherently unreliable in that they do leak. And so if you're using them as a barrier from a high pressure system to a low pressure system, you want to be really careful how you're using that. Diesel product air cooler tube ruptures. Again, tube ruptures with air coolers, you can have flammable materials that are coming in out of a tube, then a fan pushes them around. You can have all sorts of problems that go on. Also, a lot of these air coolers are elevated, fighting the event, where the isolation valves, controlling them afterwards can be really critical. So these are the kind of things you want to bring out during a HAZOP study. I remember one we were looking at for a fin fan cooler, and the only isolation valve that was practical for isolating the release was right next to the cooler on the platform. So getting to that during an emergency, especially if a leak occurred, if found an ignition source and there was a fire going on, could be really challenging if you're trying to isolate the fuel source and mitigate the event. Bottom one, pump seal failures. A lot of pumps are now being installed. People are putting the extra money up front to prevent problems later with dual tandem seals and also monitoring devices and better quality seals so that it decreases the likelihood of this, but you still have to be very careful. A seal failure, often if you're looking at a refinery or other types of process facility, can result in a fire condition, but you also, during the HAZOP study, want to look at what else is laden in that, that flow stream. Could it be H2S or some other toxic material? Let's talk about common mode failures. These can be really critical. The diagram that you see on the left is a common push-pull system for a blanket gas on a process vessel. In this case, you got a 30 psi design pressure, normally operating at 10, levels controlled, you got a pump coming out, and pressure is controlled with a 70 psi source, and when you need to make up pressure, and also it bleeds to vapor recovery when you need to bleed off pressure. You got, in this case, a single pressure transmitter feeding both the valve coming in and also the valve that relieves the vapors. This is something that classically a lot of people have looked at this, and when they're looking at failures, go like, okay, my inlet valve opens up, what's the impact? And taking credit for the valve on the outlet opening up to relieve pressure. You've got to be very sensitive to the fact that you're using common transmitters and controllers, and the fact that a common mode failure here can lead to pressure coming in and an inability for pressure to be relieved here through the normal vapor recovery line, thereby requiring your PSV as your ultimate protection device. So in terms of laying that out, you'd want to look specifically at your pressure transmitter failing low or high, looking at the valves themselves, opening or closing as a separate issue, not combining them together because that common mode failure could be much more important and also quite likely, and also considering these types of failures when you're looking at the safeguards. Again, common mode failures, what's one of the most important things to look at? What can go wrong at a facility? Operator action or inaction, whether it be in response to an alarm, whether it be a maintenance person who's been doing the same procedure for maintaining relief valves that's incorrect for your entire facility. These are things that need to be considered during the HAZOP study, and human errors and operator issues are paramount to look at very carefully. Let's also talk about a couple of other topics. Combining causes, I mentioned before in some of the examples where we've taken mechanical failures, instrumentation failures, and operator actions or inactions and put them in with the same scenario, in the same cause. The reason is it leads to the same consequences, and so other than some differences in probability, which you may want to consider when you're looking at a layer protection analysis or some other QRA technique, you really want to couple those together to make sure the team is focusing on the same consequence in the same type of scenario. The first example is a temperature control valve failing closed, possibly due to malfunction of the transmitter or a block valve being inadvertently closed. All three of those specific initiating events lead to the same consequences, so if it doesn't change your result and you're evaluating it properly, combining causes can save a lot of team time and also lead you to your conclusion and have much cleaner documentation as long as you're properly considering all those different failure modes. Also, the same cause in multiple locations. I don't know how many times that I've had to stop a team from arguing, is something a no-flow or a high-level type issue? It really, in a lot of cases, it doesn't matter. What I tend to want to do is document it in the area where it has the greatest impact. If loss of flow can trigger an immediate challenge of your safety limits and a potential hazard, then in this first bullet, a level control valve failing closed would be good to put in the flow area. That's kind of a logical place to do. You could put it in the level area, but in a case where its biggest impact is on flow, putting it there, doing it up front, getting it done right is going to be a good way to go. So what you want to do is not document the same scenario twice. I don't know how many revalidations I've picked up where somebody else has done it, and they have this big long discussion about a level control valve, and often if it's a sloppy job, they don't put in tag numbers properly about a level control valve failing, and they lead to this scenario. Then later on, when you get to the level deviations, they talk about a level control valve, and it leads to different consequences. And you're thinking it's a different level control valve, and then you're going back to research it, and you're really finding out that they're really talking about the same device. They've just done a very poor job in documenting it, and doing it twice, especially if it doesn't match, really confuses the revalidation. It doesn't do the job any better. In fact, it's worse by extremes, as a matter of fact. So doing it once, and if you have to, referencing back to a previous scenario where it's evaluated properly and thoroughly is a great way to go. Now, there may be some exceptions, but for the most part, documenting it once and only in one place works 99% of the time. And also, what we find works best is we usually take the flow deviations, the no flows, more flows, and misdirected flows first. Those tend to lead to the best conclusions and also have the biggest impacts. Completeness checks. This is something I like to do when I do a HAZOP study. Even though up front we use a highlighter, define the node, And then we use that to explain it to the team, and then we go through on a cause-by-cause basis to do the HAZOP study. On a separate P&ID, I'll usually leave it blank, and after we do all the deviations associated with a piece of equipment, I'll usually check it off, and at the end of it, and I'll usually involve the team, I'll review the entire node with the team, re-highlight the node just to make sure that there's a complete job done and that we've picked up all readily identifiable failure modes associated with equipment. Again, that's a key thing in terms of verifying that you've done a quality job for a HAZOP study. Let's talk about operating modes. This is something I mentioned before that can really wrap a team around the axle in terms of confusion, them overthinking the scenario. A typical example would be a reactor system where you're switching back and forth as you're regenerating one. Also a reverse osmosis system if you're switching back and forth again during a regeneration phase. And a lot of times there's a lot of manual valves or remotely operated valves that have to be sequenced to flip from one to the other. And the sequencing operations, the different configurations of valves, if you approach it with, let's all think about normal operation, let's all think about regeneration mode, let's all think about these other modes, it really makes the team rethink the same hazards over and over and over again. So what I find works well is to really a simpler approach where you look at each specific equipment like you would for any normal process that's operating 100% of the time, and you look at the component and then you ask the team, what's the worst operating mode for this particular component and failure mode? And then you document that. And sometimes they need to look at a couple of different operating modes, but when it's all said and done, we usually do a very good, thorough job. You know, you've looked at all the equipment, you've looked at all the operating modes, and then you've documented the ones that make sense and have an impact. So we usually just put it in the cause, in capital letters, and these are some examples of that I put on the screen. Other things that are very operating mode dependent are fired heaters. A good percentage of accidents at facilities like process facilities that use fired heaters are associated with that, whether it be startup, shutdown, reduced firing conditions, load changes, whether you've got alternate fuel compositions. Sometimes they'll switch from oil to natural gas to refinery fuel gas. All those things tend to be potentially problematic. The system's being reconfigured, and you have to be really careful about the operating modes that you're looking at. Startup especially, looking at the procedures, talking to the team, this is the most common time for accidents, so this is where you might want to do a procedure level review and make sure that you discuss all those different operating modes with the personnel on the team very thoroughly. The last one, it's an oddball, but I've seen this happen maybe 1 in 20 heaters. Somebody's got a non-combustible that's being blended in with the fuel gas going into the heater, or sometimes it's injected directly into the firebox or into the flue area. Sometimes it's done for getting by so they don't have to do separate permits for getting rid of some sort of waste gas stream. Sometimes there are other reasons for doing it, but you've got to be extremely careful in a situation like this because under low fire conditions for a heater, if you get a high concentration of non-flammable gases going into the heater, you can cause a flame out and buildup of whatever flammables are there to a concentration where you can cause heater explosions. These things are things that you want to be especially careful of if you're facilitating a HAZOP study. So defining the causes up front and before the team, as we talked about in our timeline earlier, is really critical, and it saves a lot of time. We've talked about ways to do that, the kind of causes to look at, and I've even given you some patterned words of typical causes. Probably about 95% of anything you'll see for a HAZOP study has been in this presentation in terms of how to deal with it, how to spell it out, and really getting that template together so that when you get that team together, you've got, as a facilitator, you've got a mechanism to make sure that you do a thorough job for at least all the basic stuff that you can identify up front. It helps keep the team focused, and it really helps you keep the team moving as you're doing the facilitation. Now, another part of that that's heavily equipment-oriented is defining the safeguards. As you remember, we did talk about how to deal with consequences in Module 2. defining the safeguards is something we want to do right now. A key thing to think about is timing and the priority for the safeguards. The first thing you want to do is talk about eliminating the causes and then mitigating the consequences. So listing out the safeguards in a logical fashion that makes sense and does justice to that is very effective, and it's very useful if you're revalidating it later. To the extent practical, you also want to list them in chronological order. This helps the team understand what's happening and really understanding the scenario, and we'll talk more about that in a couple of minutes. Active control features, control valves that either control pressure, temperature, or level. These are things that initially can be your initial safeguard. Control features are fine to include as safeguards. It doesn't have to be just safety instrumented systems or just operator response to possibly exceeding safety limits via alarms. Active control features are fine safeguards. They're reliable. Why not include them? Reverse flow protection, if a check valve helps, list it out. Then the team can decide how reliable the check valve is based on service, design, and if it's a valid safeguard. Alarms, again, excuse me for a second. Alarms are really good to include as long as the operator has time to properly hear the alarm. Are they at the control console all the time? Have they stepped out for a minute? Can they hear the alarm? How long does that take? Then how long does it take to diagnose the event? Decide what to do? Get approvals if necessary from supervisors, and then take corrective action. Do they have to just push a button? Is the action clear? Do they know exactly what to do, and are they trained? Do they have to go out in the field to turn something? Is it a 30-inch valve that might take a little bit to close? These are things that have to be considered when you credit alarms. And if multiple alarms result in the same action, as I mentioned before, if one alarm is clear and the operator can clearly diagnose the event, 10 alarms may be worse. It may cause confusion. And you want to consider that during the HAZOP study. Listing multiple alarms shouldn't be treated as independent safeguards or necessarily adding to the reliability of the system if the operator you're still dependent on the operator to go through those steps to diagnose and take corrective action. Written procedures, when they're considered, make sure it's best to actually list them out and specify what procedure you're talking about, whether you're talking about operations, maintenance, or even emergency procedures. Training, if you're mentioning training, what kind of training has occurred, and ask the team, is the training adequate? Also, active protection features, safety instrumented systems, and other things that are ultimate backups. PSVs, all those are fine safety features. Also, emergency response mitigation features like fire, like deluge systems, etc. Those can also be listed. Good examples of all these for active control features: a pressure control valve designed to open and flow fuel gas. Reverse flow protection check valves, as I mentioned. Alarms, in this case it's a high level alarm. And what I like to do is also ask the team, what is that alarm doing? Where does the alarm come in? And is there sufficient time for the operator to take corrective action? So I actually use a few extra words when I'm documenting the safeguard to remind the team to be thinking about these things and only credit alarms that actually are useful for mitigating the scenario. And also don't forget, analyzers too can also have alarm features on them that can be very helpful to the operator to diagnose something and take corrective action. Written procedures and training, again, I mentioned this just generally. If you're crediting training and procedures, and also what are they looking at? Be as specific as possible. If it's surveillance of process parameters, what process parameters? What are they looking at? Also, active protection features, low flow features that are designed to activate something, and also what happens after that. I usually like to lay that out so the team thinks about it. Also, there may be discrepancy alarms and other more advanced control features. You want to bring those into play also when you're looking at safeguards. Other examples: snuffing steam, fire water monitors, all those can be brought in with respect to emergency response mitigation features. I mentioned I was going to remind you about a couple of quality issues. Scenarios really should paint a picture of the event. When you document, when you talk to the team, when you lay it out for the team, And you need to make sure that people can read that later and understand what's happening. They should have a mental picture of the accident that's occurring. Safeguards have to mitigate the consequence. A lot of people I've seen HAZOP studies that people have thrown at me that were done by other individuals where the safeguards had nothing to do with the consequences. They were just having a random discussion, and the facilitator hadn't prepared themselves properly so that they understood enough about the system to recognize that the team was just rambling on and talking about general safeguards rather than safeguards directly associated with that consequence. And also, one of the things we've been doing more and more over the years is listing safeguards as independent layers of protection. As I mentioned in some of the previous modules, HAZOP studies is one type of tool to identify hazards and address the features of the regulations and also protecting your facility. Other more advanced tools such as layer protection analysis and QRA are also available, and these things can be linked. If you list your safeguards, thinking about, are they independent protection layers? If you got multiple alarms, is it only one operator action? And usually what we'll do is list the operator action, which is triggered by one or more alarms, and then list the alarms as part of one item. Listing them as independent layers of protection can allow you to easily migrate this to a LOPA later on if you like to. So let's talk about, normally I would do this if it was a one-on-one interaction with a classroom, but let me go through some key points in terms of a quiz. True or false, basically, defining causes before the HAZOP study is a good use of time. That's absolutely true. When you've taken the time to lay it out, prepare properly, and also get the causes laid out, it saves a lot of team time, and you've also got a framework for making sure you get a good quality job done. Second one here, structuring a safeguard as an IPL can facilitate transition to LOPA. This is absolutely true. It's not only clear, it's logical, but also it enables you to build on that if you need to use LOPA to help with your decision-making process. Operator action or inaction is one of the most important common mode failures to consider. Absolutely true. That can be a root cause, whether it be an indirect cause, such as somebody maintaining a piece of equipment, or directly causing a problem in the plant. That's something that needs to be considered during a HAZOP study, and it's a potentially critical common mode failure that needs to be addressed very clearly as part of the HAZOP study. That's why we spent some time on human factors. Fourth bullet, success isn't dependent on preparation. That's absolutely false. Preparing for a HAZOP study is a lot like preparing for anything in your career. Good preparation can lead to successful results, and in this case, a tangible cost benefit by doing upfront work to minimize team time and keep the team focused too. Last one, combining causes can save time, enhance the quality of the HAZOP study, and make revalidation easier. That's absolutely correct. Now, there are cases where you want to split them up, and we did talk about common mode failures, but generally, combining the causes that lead to the same consequence makes a lot of sense. All right, I'm going to come back to this in a few minutes, and what I'd like to do is switch over to the workshop, and I'm going to lead into that, and we're going to go to Module 4B. Okay, very good. Nicole, are you there? All right, you see that? Okay, if we start deviating, just let me know. All right, so what I'd like to do is, again, this is a little challenging because of a webinar type situation, but I want to lead you handhold you through a little workshop that kind of emphasizes the cause definition and also node definition and also cause definition too. But first, I want to remind you about some key issues with respect to node selection. Nodes, or the sections that you put together, are typically defined before the PHA system sessions. I have seen cases where the facilitator walks into a HAZOP study with a blank sheet of paper and then talks to the team and says, "Oh, let's start defining our nodes." That basically blows the better part of a day. and it's very ineffective. It goes around in circles. And the key thing is a lot of times the team isn't very experienced in doing the HAZOP study, and as the facilitator, as a trained facilitator, you know what to expect and how to set it up properly so it can be effectively revalidated later. Nodes typically begin where feed enters the plant and follows the process through the product leaving the plant. Nodes include major vessels or equipment and the process lines between. And also, you may want to cover auxiliary systems in a separate node. And as I mentioned previously, make sure the nodes are as large as practical. What you want to do is when the team has to consider those process dynamics and what goes on at the facility, you want to make sure that they think about similar events at the same time. Okay, some good examples of node selection. On your screen, you see a blue vessel on the left on level control with pump out on the bottom, going through a heat exchanger and through the level control valve, and then into another process vessel. The areas in blue basically are undergoing a common function. If you're talking about level fluctuations in the tank, well, things like the pump failure, things like valve failures, those are associated with that. If you're talking about the upfront process vessel and equipment, if you're looking at pressure issues, well, closing off a valve downstream of a pump can lead to a pressure issue. Temperature issues, if you're talking about a heat exchanger, whether you're talking about a cooler or if you're exchanging with another process fluid as an economizer, these are things that are looked at with the temperature deviation. So coupling them together like this allows you to go through the HAZOP study deviations very effectively, and grouping them like this really helps out a lot. A really bad example, and I have seen lots of these when I've revalidated other people's work, has been when they take each process component and make a separate node out of them. They look at the blue vessel, the vessel in blue on the left, and they go like, okay, this is something that we need to look at level issues, pressure issues, temperature issues, etc. Then they go down to the pump and run through the same process, and they're essentially looking at the same issue. And the worst part about it is a lot of times they're not connecting the dots and making sure that when they talk about the same issue, they're actually getting the same results. So again, coupling together areas where you're looking at the same kind of process dynamics really helps out a lot. A very effective example that is a little bit off the wall, and you get a little bit of a pushback as a facilitator, but you just got to tell the team to bear with you and try it out, is something like you see here. In a situation like this where you've got liquids coming in, a feed vessel, pump, and then flow control going through an economizer exchanger, through a heater, and then into a reactor, and then back to the economizer. These are things that we found. This is a typical setup for, say, a hydrotreating plant, and we found that when you do this, making that first area as one node actually makes a lot of sense, and it works very well. You deal with pressure issues in the push-pull system on the feed drum. You're dealing with level issues on the feed drum, the pump and flow control valve, the no-flow issues that also translate into level. And in these typical flow streams, especially at the front end of a hydrotreater, there's not a lot of control required. So there's not a lot of active components between that flow control valve that you're looking at and the reactor effluent. So in a situation like that, you really find out that you can go through that entire area for the HAZOP study very simply. You're talking about the same kind of consequence phenomenology at the same time, and it's very clean and it's easy to find stuff later. So think about process dynamics, what's happening with the system as you're defining the nodes. Now you also notice that beneath the heater, it is a fired heater, there are some red lines. Typically what we find is for a fired heater, the fire control system, any sort of flow of the combustion air, all those things are good to address as part of a separate node. Other node selection tips, keep colors simple. Again, we do a lot of work over long periods of time with facilities, and over the years, and especially if we're picking up revalidations where somebody else has done the HAZOP study, if they use the 20-color highlighter set, a lot of times over the years, those colors tend to get affected by UV light. They change their tone, and it's really tough to tell any differences after a certain period of time. It gets even worse if you take that and put it on a scanner and they scan the drawings, even with a color scanner, the color doesn't really match the initial ones. So keep it a few basic colors so they can be differentiated later. Also, we tend to highlight PDF files so they can be useful later. And in fact, that's the one that's being used for our little workshop this morning. So let's do a little exercise for defining the nodes. And what I'm going to do is switch over to that PDF file and just the first page, if you wouldn't mind. Good. All right. You got that? Okay, great. All right, so this is a small example from a refinery process. Basically, you got feed coming in through reactor, through heater, then reactors, and basically you got a process separator as it's coming out of that. Feed comes in on the upper left-hand side, and basically the product is going out on the right-hand side. That's what you see on your screen. So what I would do with this in terms of defining the nodes, and that's what you see on your screen now in yellow, is basically take the feed coming in from the upper left-hand side on flow control, going through your heat exchangers that economize the heat from the reactor effluent, and then to heater 001, and then to the inlet of the reactor. That works really well because you get a few active components, and you get very similar impacts on all your heat exchangers as they come in. What I would do with that for a second node is to follow the process and basically take the reactor itself and the effluent going back to the heat exchangers that you will have just discussed with the team, and then finally to a fin fan cooler on its way into the product separator. That's the main flow of the process. After that, I would take it and I would take it from the product separator and really look at that. The team's really familiar with the feed coming into the unit, picking up heat and going into the reactor, coming out, releasing its heat, going through the fin fan cooler and also the product separator, and that's where I would put the third node, and that's what you're seeing in pink. The fourth node is, since the team's already talking about the product separator, and again, another thing you want to keep in mind when you're defining the nodes is how do you control the team thinking about process dynamics and hazards associated with the system. So as much as possible, you want to follow the process and avoid jumping around. Sometimes you can't avoid that because you've got to pick up similar types of events, or in some cases, gosh, if you're discussing a lube oil system for a very large process unit, you may have multiple lube oil systems that have similar functions. Maybe that's a utility system that you save to the end and then do one and do it right and then copy it over and do them all with the team at the same time for efficiency and while they're thinking about it. That's another way to pick up time and also do a really good quality job. So if you've just finished the product separator, the next logical thing to do is to the separator knockout pot, D005. That's the area that you see in blue. I would make that node 4. Another thing that we've got is we got other materials going through the heater. It is separate, basically a separate process, but this is a good time to pick it up. And I wouldn't separate out the material going into the heater and the material going out of the heater. This is a good time to pick up the whole thing. And since you've just discussed both parts of the heater, node 6 I would make that's in yellow on the lower left-hand side, I would pick up the firing system next on that and make that one node. And for this type of process, the last piece is basically in the upper right-hand side, which is associated with the suction knockout pot. These are the sort of things that would be picked up last and basically complete this portion of the process. Notice that we've been defining the nodes on the process flow diagram. Even though the P&IDs have more information in terms of understanding the process and setting it up so that you've got dynamics that you want to work with the team on, this is very effective. And also allows you to focus as the facilitator, constantly seeing the big picture so that you can guide the team. As a reminder, the HAZOP facilitator, you've got to be talking about what you just discussed with the scribe sometimes, or make sure the documentation's in tune, discussing things with the team, and you've also got to be thinking ahead so you can properly lead or guide the team and facilitate that HAZOP study. understanding the process and really keeping track of where you are with the process flow diagram is very helpful. Whenever I'm facilitating a HAZOP study, I'll usually have both pre-noted right in front of me so I can keep track of where I am and where I'm going. All right, so that concludes our discussion of nodes, or that's our workshop in terms of how to set up nodes. Now, what I'd like to do best is talk about defining causes. And this is a small portion of a process where you've got on the left-hand side. Nicole, do you have this on screen? Okay, good. It's a small tank where you've got on level control where the vapors are going off to an air cooler, a trim cooler, and then to another process vessel where you've got, in this case, water and hydrocarbons being separated, water coming off to the boot on the left and hydrocarbons coming off to the boot on the right. So what I'd like to do is go through that and first of all talk about what the nodes would be, and then secondly talk about what kind of causes would make sense. Okay, the first node that I would pick up on that would be D906, and the level control off of that going off to the hot separated liquid on the lower right-hand side. The other node that I would define for that is the vapors coming off of D906 going through XF913, X914 into D907, where they get separated. You may have some vapors coming off. That's not shown, by the way. And then you've got some water and also some hydrocarbons coming off the bottom. So I'd like for you to use that diagram, and what I'd like to do is to run through some basic causes. So what I'd like to do, Nicole, is go to 4D. All right. So this is the exercise we're doing on key causes. All of you who are tuned into the webcast have a physical copy of that small P&ID. And so what I'd like to do is hold your hand through the little workshop and define some causes here. All right. So node 1 is D906 in the level control valve. So let's talk about some no flow items. What sort of things would you look at as a team for no flow? Well, this is really a very simple one. The major active component there, and by the way, another thing you need to do for a HAZOP study is separating the important from the unimportant. On this diagram, there's lots of valves, there's lots of manual valves, and there's also a lot of valves that are shown for instrument loops. But recognize when you're looking at a valve on a level bridle, closing that, compromising that, it's going to have the same effect as if the level transmitter fails. If you're looking at a level control valve, that valve closing is going to have the same effect as if the block valve is closed. So combining those, simplifying it, and looking at the things that are really important is absolutely critical. So for D906, you'd look at that, and then you realize that that block valves in the bridle really aren't going to add to it because you're going to cover the level transmitter. The block valves around the level control valve 15 aren't going to do much more. You're going to be looking at that level control valve failing closed. So really, from a no-flow perspective, you're going to capture everything with just by a single scenario, LCV015 failing closed, or possibly due to a transmitter malfunction, or a block valve inadvertently closed. That's going to encapsulate your key no-flow item for this. For more flow, you're going to be looking at that level control valve. By the way, you guys don't have a hard copy of this. I want you to be thinking about this as we're going through it, and I want you to work off of this drawing right here. Okay? For a more flow case, the level control valve malfunctioning open is going to cover, and of course you have to ask this, but usually the bypass valve is about the same size. It's going to cover the bypass valve being open, the valve malfunctioning open, or some sort of transmitter failure. And I usually work it back to the transmitter because sometimes the controller can, there can be multiple controllers, and sometimes it leads back to a single transmitter. So you always want to get to the root part of the control system that can fail. So these are the key scenarios that they're really going to encompass the embodiment of the hazards for this node 1 that we've defined. So let's take a look at node 2. All right, as we exit D906 again, we're looking at the vapor path through XF913. X914, and then over to D907, and then we got some level control valves coming off of that. Well, following the process, again, is really important for the team's understanding. What are some of the no-flow things that can occur? Well, XF913 can undergo fouling. You want to ask the team to think about that. There's also block valves upstream and downstream of 914. And also, as you exit D907, you got level control valve 010 on the hydrocarbon side. And I like to, by the way, there's a typo here, LCV 907. That really should be LCV 011. That valve can be now failing closed, also to cause no flow. So the key no flow cases that I'd want to look at for node 2, and they're written out here. By the way, we'll be emailing a copy of these results from our workshop to everybody who's participating here, in case you're trying to scribble these down quickly. It's the effluent air cooler fouling, the block valve upstream of the trim cooler closed, the block valve downstream closed, LV10 malfunction closed, or LV11 failing closed. Now, a couple of key things that I'd like to bring out here. For the first no-flow case, a lot of times when dealing with clean service, fouling of equipment is very unlikely. And so developing a full HAZOP scenario where you start documenting all the consequences and finally concluding that it's a non-issue is really, in many cases, a bad use of some very valuable resources, which is your HAZOP study team. So if it's a clean service and it's not very likely that fouling can build up enough to actually cause enough compromised flow to really precipitate a hazard, why not just say that up front? Get the team to endorse it. Make sure you talk to them about the things that really are important, which are their procedures, how they monitor it, how they check for fouling, are they monitoring the overall process efficiency, and that's what you want to verify. And if that's the case, keep the documentation simple. So in a lot of cases, I'll just basically take an unlikely event or something that really doesn't result in a consequence and nip it in the bud early and just verify how they deal with their system with the team. The second item on that list, a lot of times you'd kind of combine block valves. If you notice when we were talking about level control valve in node 1, we really didn't talk about the block valve upstream or the block valve downstream because it really didn't make a difference. Here you need to be sensitive to design pressures and do things make a difference. Combining stuff is great, but you never want to lose sight of the fact that you may, in this case, have to pick up on the fact that XF913 is designed for 850 psig. D906 is also designed for 850 psig, but X914 is only designed for 550 psig. That's not that much of a difference in pressure, but you don't want to presume as somebody who's not the designer of the system or the operator of the system. You're the facilitator getting prepared for your HAZOP study. You don't want to presume that it's fine. You want to at least set it up so that it prompts the question to be asked if it's blocked downstream, and can X914 be pressurized above its design pressure even though the other pieces of equipment are just fine and happy. So that's why you might want to separate it here. The upstream consequence and the downstream consequence may be very different. And also, you want to bring out here, I see a PSV on D907, but I don't see one on D906. So if you close those valves, does it block off a communication path for overpressure protection? Do you need to talk to the team about car sealing open, locking open those valves, or some other means of overpressure protection? These are all things that need to come up during the HAZOP study. And as the facilitator preparing for that HAZOP study, you want to make sure that you set it up so that it prompts the questions, and because you can't always count on the team to be really thinking outside of the box. Keep in mind that as a seasoned HAZOP study facilitator, you're used to thinking about how can things go wrong. Your team in operations or design are usually thinking how to make things work. That's a totally different way of looking at the world, and your perspective on this, if you set the HAZOP study up properly, is very valuable to them for good quality HAZOP. The last two I want to bring out the fact that, first of all, we are coupling in the transmitter, human error, and mechanical malfunctions because they lead to the same consequence. Again, you'll want to challenge the team during the session if that's not the case. But one of the things that has caused confusion with the teams in the past is usually valves that are especially if they're air operated, have a specific failure mode if the air operator is removed or if you lose instrument air. A fail closed valve will have a spring. It'll close the valve if you lose the instrument air. A fail open valve will have a spring that opens the valve if you lose instrument air, or some other mechanism of achieving that function. So to avoid confusion, if a fail closed valve is closing, usually you'll say it fails closed. If it's a fail open valve, its failure mode, preferred failure mode is fail open, and if it's closing, usually you'll say malfunction closed, and that avoids confusion with the team. Okay, so let's talk about more flow cases. In this particular case, you've got, there's not a whole lot more flow that can go on with XF913 or X914, and you could look at the bypass valve on X914 as possibly a more flow case. However, keep in mind that when you bypass a heat exchanger like this, the biggest impact may be temperature. So in this particular case, you will think ahead and realize that it might not be a flow issue, but more of a temperature issue. So you're going to hold off on that bypass valve being open until you're ready to talk about temperature. So key more flow cases associated with this node might be associated with those level control valves. So for a more flow case, we've got LV10, which is a fail open valve, failing open. We got LV11, which is a fail closed valve, malfunctioning open. Both of those causing more flow, and also picking up if the bypass valve